Alright guys, welcome to the second installment of me sitting in a dark room talking to myself. I brought some better equipment into my dark and lonely room again this time, so we'll see how it goes. For the second half of our talk about limits, we have sections 2.4 through 2.6. Section 2.4 is the formal definition of a limit, which is not unlike the definition I already gave last time, but it's a little less tedious to work with. I don't have to find a bunch of sequences or anything. And it uses Greek letters, so you know it's good. So I'm going to write that out really fast here. Don't blink. So what we have is the limit of a function f of x as x approaches c is a real number L if, for any margin of error epsilon greater than 0, there exists an input tolerance delta greater than 0, so that whenever x minus c is less than delta, we have f of x minus L is less than epsilon. Now I've mentioned it before, but what we really have going on here is this x minus c here is an interval. If x minus c is less than delta, that's the same thing as saying that minus delta is less than x minus c, which is less than delta, or x is in the interval of c minus delta up to c plus delta. And similarly for my f of x minus L here, this says that my f of x is in L minus epsilon up to L plus epsilon. So in a picture, I'm going to have some kind of a function doing whatever, and I'm going to have a c value that I want to find or learn information about. I'll have a margin of error and a supposed limit here as L. What I want to do is I kind of want to follow these guys back to the x-axis. Here I have my c down here, but what I want to verify is that the whole point behind the definition here is, regardless of what margin of error I use, I'm going to be able to find an appropriate delta so that any x value that falls inside of this interval down here is for sure going to land inside of my target range up here. So what I want to do here is I want to decide how big my delta is going to be, where my interval is going to be, how far away from C are going to be the edges of it. As you can see by the picture here, this point here, we'll call it B, is outside of the interval. It's too far away from C, because if I were to use an appropriate matching distance on the opposite side of C, and I map it through my function, I end up landing outside of my target range, and that's not good. So what I want to take away from this picture is, given a margin of error over here, I should be able to find an appropriate delta that I can calculate over here. And in terms of pictures, delta is always going to be the smallest half. But keep in mind that when I say delta, delta is the distance away from C here. It's not going to be the actual x value, it's however far down I move from C, or up, as the case may be with different pictures. Now the question is, how do we use this? I mean, we can have some of these techniques that we use to calculate some precision problems, but what I care about as a mathematician is the formal definition is what we need in order to have a concept of a limit. So this definition is the source of all those limit laws we talked about in section 2.3. It's needed in order to prove all of those, to make sure that those are always going to be true, regardless of my function. But what I can also do is I can use it to verify an existing limit value that I think I have. So for example, I would want to verify that the limit as x goes to 3 of 4 minus 2x is equal to negative 2, like I think it is. If I use direct substitution, I indeed am going to get negative 2, because I'll have 4 minus 2 times 3, which is equal to 4 minus 6, which is negative 2. But let's say I'm uncertain about things, and I just want to verify this. Now, according to the definition I have up here, I want to be able to find a delta, that's going to guarantee whenever x values fall inside of this delta range, I can satisfy this inequality, then my y values, my function values, are going to fall inside of my epsilon range. So let's see if we can make sense of that. Now, when I want to do a verification thing like this, or a proof of my limit, I always want to start off exactly the same way. I'm going to start off with two lines that are always the same. I'm going to say fix epsilon greater than 0, and I'll follow it up with suppose this guy right here, my x minus 3 is less than delta. X minus 3, 3 is less than delta. But I'm going to leave myself some space here, because I want to find out what this delta is that's going to satisfy my definition. Then, I'll take my f of x minus L portion, 4 minus 2x minus parentheses negative 2, and I'll simplify it. I won't write the less than epsilon part yet. I'm going to save that for the very end. So this simplifies to 4 minus 2x plus 2, which is 6 minus 2x in absolute values. Now, my goal for these problems is to try to get my x minus c to pop out so that I can replace it with a delta. But I don't quite have that. I don't even have a 3. The best I can do here is factor out a 2 to get 2 times 3 minus x, which is kind of backwards of what I was supposed to have up here. Fortunately, though, this is inside of an absolute value, and so this value is exactly negative 1 times the value I have up above, so I'm just going to flip it without any repercussions, because it's inside of an absolute value. So this is equal to 2 times x minus 3 instead. And since x minus 3 is less than delta here, this is less than 2 times delta in place of the x minus 3. Now what I'm supposed to get here is equal to epsilon at the end. So it looks like if I chose delta to be a half of epsilon, then my problem will be satisfied. So I'll put a period here and then I'll rewrite it. Or reread it, I should say. This says fix epsilon greater than 0 and suppose that x minus 3 is less than delta, which is equal to epsilon over 2. Then my f of x minus L is 4 minus 2x minus negative 2, which is equal to, after some simplification, 2 times 3 minus x, or 2 times x minus 3, which is less than 2 times delta, which is equal to 2 times epsilon over 2, which simplifies to epsilon. So in the end, I have read my f of x minus L is less than epsilon. And that's exactly what I wanted to happen. So my limit has been verified because I have demonstrated that it satisfies the definition of the limit. Now this isn't usually included, but I'm also going to toss in a slightly more complicated example. Instead of having a linear equation, we're going to have a parabola. Now I want to verify, I want to verify that the limit as x goes to 2 of x squared minus x is equal to 2. Sure enough, like before, if I use direct substitution and I plug in 2, I'm going to get 4 minus 2, which is equal to 2. But only on days that end in y. So let's see if I can remember what to do. I need to fix epsilon greater than 0. And I need to suppose that x minus c, that's 2, is less than delta. And that's going to be equal to something. Then, my f of x minus L, x squared minus x minus 2, I can't really simplify that further, so I'm going to factor it instead, because I really want to have an x minus 2. So, how do I factor this? I can factor this like x plus 1 times x minus 2. And I can split up the absolute values to make it look like this. They kind of distribute across multiplication. And I have my x minus 2 here, so I can go ahead and replace it with the delta like I did before. So I'll write that like this, less than x plus 1 times delta. But now I have a bit of a problem. Here I still have x's. How do I get rid of these x's? I don't know how big x is supposed to be. So what I do in this case is I try to set up more inequalities. But I make another assumption. First, I'm going to assume that delta is less than 1. Because if I'm looking for a limit of a function, if I'm looking for the limit as x goes to 2, I have no business looking at x equals 13, right? That's way too far away. That's not even close to 2. So I'm going to assume that delta is less than 1, so that my x values are no more than 1 away from 2 while I'm trying to evaluate my limit. So what I get out of that is from x minus 2 is less than delta is less than 1, which means the absolute value of x minus 2 is less than 1. Or if I split it, I have minus 1 less than x minus 2 less than 1. So from here I can solve for x. I'll add 2 to each of the 3 parts, so I'll have 1 is less than x is less than 3. And I can do one better. I have an x plus 1 down here, so I'll add another 1 to each of the 3 parts. I'll have 2 is less than x plus 1 is less than 4. Which tells me that my x plus 1 is always smaller than 4. It's also bigger than 2, but that doesn't concern me too much. So I can replace this x plus 1 with a 4 now. And now I have a simpler expression. I can set that equal to epsilon. Which tells me that if delta is equal to epsilon divided by 4, I'll have what I need. So now if I reread this, now that I've done my work, I should have fix epsilon greater than 0 and suppose that x minus 2 is less than delta, which is equal to probably not epsilon over 4, even though that's what I found because I made a further assumption. So I'll say the minimum value of 1 and epsilon over 4, just in case somebody gave you a really big epsilon. Then my f of x minus L, which is x squared minus x minus 2, is equal to the absolute value of the factor version, x plus 1 times x minus 2. I can replace the x minus 2 with the delta, and I found that I could replace the x plus 1 is no bigger than 4. So I have my f of x minus L is less than epsilon, as desired. There are extra versions of this formal definition of the limit for cases where your x values go off towards infinity, or when your function values grow in an unbounded fashion, kind of like when you get close to 0 for the function of 1 over x. But they're not too different. They're just slight rephrases of the existing definition, so we don't need to worry about them separately as much as other things. Next up, we have the notion of continuity. I've mentioned this before in the previous lecture because I kind of needed it. continuity is what gives us all of the best things about solving limits, as horrible as they are, like direct substitution, which is our favorite. And I've stated the definition before, so I'll state it again. A function f of x is continuous at x equals a if the limit as x goes to a of f of x is f of a, or in other words, the limit is equal to the function value, which is the best possible scenario when doing anything with limits. But that definition is only for a single point. If I'm continuous at several points, it's similar. I just say that it's true for every value on an interval. So a function f of x is continuous, or possibly on an interval. I wrote an open interval, but we can also talk about closed intervals. If the limit is equal to the function value for every value in that interval. So, given those definitions, I mean, we have easy functions which are continuous virtually everywhere. I listed them all out last time, but we have things like polynomials and rational functions, exponential functions. Those just work all the time. Which is why we love them so much. But I'm curious to see if there are functions which are less continuous. Does there exist a function which is continuous nowhere? Can I find a function which satisfies the first definition but not the second? Is there a function which is continuous at exactly one point and nowhere else? The answer to all of those questions is actually yes. So let's find out what that function is. So first up, I have a couple of facts that I want to address for this problem. Is we care about the difference between rational numbers and irrational numbers. Rational numbers are the ones that we can express as a fraction or a ratio of integers. 1/2, 1/3, 47/15, stuff like that. But irrational numbers are numbers which cannot be expressed as a fraction or a ratio of two integers. And the classification of irrational numbers are numbers whose decimal expansions are non-repeating and non-terminating. Every other number which has a decimal expansion which repeats or stops is a rational number, because I can actually find out what that fraction is. So, there is a property. Rational numbers are dense in the real numbers. And what that means is any interval you take, no matter how small, contains a rational number. And it turns out this property is going to be instrumental in creating one of the worst functions you'll ever see. And here it is. D of x, assume whatever D stands for yourself, it will be 1 if x is rational, and it will be 0 if x is irrational. Zero, 1. So how this works is pick any epsilon greater than 0 for your margin of error. I'm going to pick 1/2. Then what happens? Well, if I start using irrational numbers, then I'm supposed to have an input tolerance. And any time I plug in a number inside of this interval, it needs to land within the margin of error. But since every interval contains both rational and irrational numbers, that means no matter where I place my limit, up here or down there, I'm going to have a bunch of numbers falling outside of my target range. If I think my limit is up here close to 1, then I'm going to have a bunch of irrational numbers which go to 0 through the function, which fails the definition. If I think my limit is down here at 0, then I'm going to have a bunch of rational numbers which evaluate to 1 and fall outside of my target range. So this is a function which is continuous nowhere. And in fact, it's even worse than that. The limit exists nowhere on this function. And there is a variation of this where you can make sure that it's continuous exactly once. And I'm going to use the same kind of thing. But what I'm going to do is I'm going to try to make these two lines intersect each other once. So I'll call it D party hat of x, because we know how to have fun. This will be x if x is rational, and it will be 0 if x is irrational. Doing this has the added benefit of guaranteeing that no matter how small I fit a margin of error, I'm going to have this nice little box here that's going to satisfy my definition for my limit. If delta is equal to epsilon in my limit definition, then we are good to go. I'm going to say then the limit is satisfied. But everywhere except for 0, this is going to have the same problem as the previous example. It's going to be continuous nowhere. But it is continuous at exactly one spot, because the limit is equal to the function value at that one spot. Now, continuous functions have some properties, and those are kind of like the properties of limits. If I have two continuous functions, f and g are continuous, then so is pretty much any combination of these functions. F plus g, f minus g, f times g, f divided by g, as long as g is not equal to 0. Constant multiples of the function, and something else, function compositions. That's a big deal. F of g of x will also be a continuous function. I suppose by symmetry so would g of f of x, but I won't need to write that. We also have the additional properties that I mentioned before when they counteract with limits, and that's basically just the direct substitution property. So another thing that comes out of continuity is the intermediate value theorem. And what that does is it tells us that we always have intermediate values, whatever that means. So I'll just write this super fast. So the intermediate value theorem says that if a function is continuous on an interval, then for any y value in between the function values of the endpoints, so between f of a and f of b, and that can go either direction depending on which one is larger, there exists a c in between a and b such that f of c is equal to that function value y. Or I should say y value. And that's something that kind of makes sense with the picture, because so if I have a function value here, a, f of a, and another one here, b, f of b, since the function is continuous, I have to connect these somehow, right? It's continuous, they must be connected. And so I'm going to have to be able to hit all the function values eventually in between the two. Now, one of the applications of this property is helping us to find roots of functions, or at least finding out if they exist. It won't really pinpoint it for us, but we'll have to use other methods for that. I'll ask a question like, determine if 3x equal to cosine of x has any solutions. And the way I want to read that is I'm looking for an intersection between these two functions. Or if I were to rewrite it, 3x minus cosine of x is equal to 0. So what does that mean? Well, that means both of these are continuous functions. 3x is continuous, cosine of x is continuous, therefore the difference is continuous. So I have this continuous function, and I'm looking for a root or a solution to this function. And what the intermediate value theorem will do for us is, if I find a spot where this function is positive, and I find another spot where this function is negative, then somewhere between those two spots, between positive and negative, I have to cross the x-axis. My function value has to be equal to 0. So I'm going to try to hunt for one of those problems. I'm going to start at 0, because that's easy. H of 0 equals 0 minus cosine of 0, which is 1. So this is negative 1. Fabulous. Now what else is easy? Let's just go ahead and do pi. H of pi is equal to 3 pi minus cosine of pi, but cosine of pi is equal to negative 1, so this is equal to 3 pi minus 1, so 3 pi plus 1. We'll notice that this first spot is less than 0, the second spot is greater than 0, and since that's positive and negative, then somewhere in between, the IVT says h of x is equal to 0 for some x in 0, comma, pi. Now you notice that it doesn't tell us where it happens, it just happens. And so one of the best things we can do with that is just start cutting this interval in half and checking the endpoints until we get a very, very small interval. And just, use one of the endpoints of that as the crude estimation of our root. Another standard kind of example we could ask about continuous functions is to try to get you to fix a continuous function. Now what I mean by that is we have a function which could be continuous, but there's an unknown coefficient that we have to try to solve for. So what we have here is a potential problem at 3. My function is equal to 2x squared minus ax for x values less than or equal to 3, but it's equal to ax plus 12 for x values greater than 3. So what I need to make sure is going to happen for this problem is that the definition of continuity is satisfied. And what that means is I need the limit to be equal to the function value. But more than that, since I have different things happening on different sides, I need to make sure that the limit is going to exist. And then it's equal to the function value. So what we need is the limit as x goes to 3 from the left of f of x to be equal to the limit as x goes to 3 from the right of f of x. And we need that to be equal to f of 3. Notice that since I have continuous functions involved on both sides, since I include 3 on the parabola half, my limit as x goes to 3 from the right is automatically going to be equal to f of 3. So I just need to make sure that these two limits right here are equal to each other. Now the limit as x goes to 3 from the right of f of x is going to be using, it's going to be using x values which are less than 3. So I'm going to be using this version. And that's an easy enough limit to evaluate. Even though I don't know what a is, I can still just plug in 3. What did I write? 3 minus. Much better. I have 2 times 3 squared. That's 2 times 9. So I have 18 minus 3a. And for the other limit, I have the limit as x goes to 3 plus, and I'm going to use the opposite side of my function, so that's going to be ax plus 12, and that's going to be equal to 3a plus 12. And these are supposed to be equal to each other, so I'll set them equal to each other and try to solve for a. So I'll have 18 minus 12, which is 6, equals 3a plus 3a, that is 6a, which I guess means that a is equal to 1. And I only had equations which are linear in a, whatever that means, so I'm only going to have this one solution. And that's it right there. That's all values of a. For our final section, we have limits to infinity, which you should be always equating in your mind as horizontal asymptotes. So what I mean by that, whenever you see the limit as x goes to infinity, or the limit as x goes to minus infinity, you should immediately be thinking horizontal asymptotes. Now, when I have a rational function of polynomials, pre-calculus has given me a nice little shortcut for this. Suppose I had 3x to the fourth minus x squared plus 17 divided by negative 2x, I'm going to put a box here, minus 6x plus 12. And my question is, does f of x have any horizontal asymptotes? Well, if the powers of the top and the bottom are the same, then I'm going to use the coefficients of the highest powers. Y equal to 3 over negative 2. If the power on the bottom is less than the power on the top, there will be no horizontal asymptote. And then if the power on the bottom is greater than the power on the top, my horizontal asymptote is y equals 0, always. But this doesn't help me when I don't have rational functions of polynomials. If I have stranger things, then I have to deal with different techniques. So I'm only going to do one example because it covers basically everything from this section. As I'm going to look at the limit as x goes to infinity of x minus the square root of x squared plus 1 divided by 4x plus 3. Now if you tried to use the above shortcut, you would be definitely wrong, because neither of the horizontal asymptotes, there can be more than one, is equal to 1/4. But my process for all of these is always going to be the same. I'm going to look at the highest power in the denominator and divide that from the top and from the bottom. So I'll multiply the top by 1 over x and the bottom by 1 over x. And when I distribute, I'm going to have 1 minus the square root of x squared plus 1 over x all over 4 plus 3 over x. And this process is essentially exactly why the above shortcuts work for the rational functions of polynomials. What we see here, I encounter a bit of an issue. I need to move the x inside of the square root in order to simplify that. So I'll say all my x values are positive, so I don't have to worry about any square root troubles. So I'll just say that x is equal to the square root of x squared. And I'll make that substitution. Now this has the advantage of allowing me to combine my square roots because they're related to each other by multiplication or division. Square roots will not distribute across addition or subtraction, but they will work across addition or multiplication and division. So here I have the limit as x goes to infinity of 1 minus a big square root. X squared over x squared is 1 plus 1 over x squared all over 4 plus 3 over x. But now when I apply my limit, if I try to plug in infinity for x, I'm going to end up with 1, for example here, 1 divided by extremely large numbers. So that's going to go to 0. That's always true. 1 over very big numbers goes to 0. So this is equal to 1 minus square root of 1 plus 0 over 4 plus 0, which is equal to 0 over 4. But something different will happen when I go to negative infinity. I'm going to start off the same way. So I'll go ahead and copy the first step right here. This is 1 minus the square root of x squared plus 1 all over x all over 4 plus 3 over x. But I have an additional concern here because x is going to negative infinity, which means my x values are negative, all of them. But when I do the square root of x squared, I end up squaring those x values before taking a square root, so this is always positive. So in fact, the square root of x squared is equal to the absolute value of x. And in the long definition of absolute value of x, this is equal to x if x is greater than 0, and a negative 1 times x if x is less than 0. Because if x is negative, the absolute value forces it to be positive, essentially by multiplying it by an extra negative 1. So this says that the square root of x squared is equal to negative x. Or I can replace this x with a negative square root of x squared. So I have 1 minus square root of x squared plus 1 over negative square root of x squared all over 4 plus 3 over x. And when I simplify that, I have 1 minus plus 1 plus 1 over x squared all over 4 plus 3 over x. So now my limit looks like 1 plus the square root of 1 plus 0 over 4 plus 0, and that's equal to 2 over 4, which is 1/2. So we should always check both sides of the real line if I'm looking for horizontal asymptotes, because they can be different on the left side and on the right side. So some additional facts that will help you evaluate some of the weirder limits. The limit as x goes to infinity of arctangent is equal to pi over 2. The limit as x goes to negative infinity of arctangent is negative pi over 2. But also the limit as x goes to infinity of e to the x, or in general any exponential function, that's not even an asymptote, that's infinity, it goes up forever. But the limit as x goes to negative infinity, that actually goes to 0. That concludes the second half of the limit lectures. So next time we'll be talking about the definition of the derivative, and after that we'll actually move on to the derivative rules before actually attempting new material for this course.